Welcome to paper 32. This is the mechanics paper in the June 2025 A-Level Maths series. Question 1 is a straightforward SUVAC question. We get the initial velocity, which is 15, the acceleration is 2, time is 4, and we're trying to calculate the velocity, so we're going to use v equals u plus at. Substituting the values, v will be equal to 15 plus 2 times 4, which comes out as 23 meters per second. For part B, using F equals ma, we know that the force less 400 will be equal to the mass, which is 800, times the acceleration, which is 2. Adding the 400 to both sides, we can work out that driving force is 2,000 newtons. That's question 1 done. Question number 2, we're going to resolve vertically in A. So the forces going up will be equal to the forces going down. The forces going up will be the normal reaction force plus the component of the pulling force in the vertical direction. That's 5 sine alpha. That's going to be equal to the forces going down. That's 2g, the mass is 2, times that by g to find the force going down. Bring the 5 sine alpha onto the right hand side. We know that sine of alpha is going to be 3/5, and so 2g minus 5 times 3/5 is 16.6 newtons. For part B, the motion after the force is removed, well, the box is going to decelerate until it comes to rest. For C, the removal of the 5 newtons means that the only forces in the vertical plane are the 2g force going down, so 2g for C. And for D, we're going to use F equals mu r, so 0.2, that's our mu, times by 2g, that's r, gives us a frictional force of 3.92. That's the resistive force slowing down the motion. Using F equals ma, that resistive force is going to be 2 lots of the acceleration, so the box is going to be accelerating at 1.96. However, that's in the negative direction, so when we use A, I'm going to use negative 1.96. The initial velocity is 4, the final velocity is 0, and so we're going to get 0, v squared equals u squared plus 2as, 0 squared equals 4 squared plus 2 lots of negative 1.96 times s. Do a little rearrangement, bring the s onto the left and divide by 2 lots of 1.96, and we get s being 16 divided by 2 times 1.96, which is 4.08 meters. Many possible correct answers for E. I've gone with the frictional force being constant in this one, but you could have picked other ones as well. So the box being a particle, etc., etc. Question 3a, I'm going to jump in with F equals ma. We know the mass is 0.5. We know the acceleration is 2i subtract 2.4j. So the frictional force will be 0.5 lots of 2i minus 2.4j, which simplifies to I subtract 1.2j. For part B, we have an initial velocity of negative 7i plus 7.8j. We know that the time is going to be 2. The acceleration is going to be 2i subtract 24j. And we're trying to calculate the velocity. So we're going to use v equals u plus at in 2 dimensions, so RV is going to be equal to negative 7i plus 7.8j plus 2i minus 24j lots of 2. Expanding that out and simplifying it, we get that v is equal to negative 3i plus 3j. For C, well, negative 3i plus 3j, that's northwest, so that's a bearing of 315. If you didn't spot that, you can do a little bit of trig, do inverse tan of 3 over 3, and then add it to whatever you need to end up, or subtract it from 360 to end up with 315 being the bearing. For part D, our initial velocity, negative 7i plus 7.8j. The acceleration, 2i subtract 2.4j. T equals 5, and the vector O to A is the displacement that we're trying to find here. So I'm going to use S equals ut plus a half at squared. So S equals negative 7i plus 7.8j times by 5, plus a half of, and then 2i subtract 2.4j lots of 5 squared. Expanding that all out, we end up with negative 35i plus 39j plus 25i subtract 30j. So our displacement, our vector from O to A, is negative 10i plus 9j. All right, question number 4 gives us the displacement r. When t equals 4, we can just substitute 4 in. So 4 times 4 to the power of 3 over 2 lots of I, subtract 4 squared lots of j. And that's 32i subtract 16j. If you're using column vectors, that's absolutely fine, as long as the question doesn't say give your answer in terms of A, I, and j. For B, the distance from P to O at t equals 4, essentially we're working out the distance of sort of the hypotenuse of a triangle with a base of 32 and a height of 16. So 32 squared plus negative 16 squared square rooted will give us 16 root 5 meters. For part C, to find the velocity, we're going to find the change in the displacement over time. So we're going to differentiate. Multiplying by 3 over 2 gives us 4 times 3 over 2 is 6. Subtract 1 from the power is t to the half, lots of I. And then differentiating t squared to 2t, so minus 2t lots of j. Part D, the acceleration, we're going to differentiate again, multiply by the power, subtract 1 from the power. 6 times a half is 3, subtract 1 from a half is negative a half, and then subtract 2j. Now we know it's perpendicular to a line with a gradient of a third, so the negative reciprocal of a third is minus 3. So if we take the gradient of our particle, that's minus 2 over 3t to the minus a half, that's going to be equal to minus 3. Here's a few ways you can tackle this. Here I've multiplied both sides by 3 and I've brought t to the negative half to the top and made it t to the half. Divide both sides by negative 2, t to the half is 9 over 2, square both sides, t is 81 over 4 seconds. If you've done that as a decimal, that's absolutely fine. All right, question 5, projectile motion. I'm going to look at the horizontal direction to begin with. The initial velocity is 14 cos theta. The displacement is 40. We've got to work out the time. Of course, there's no acceleration in the horizontal plane. Acceleration will only come in the vertical plane due to gravity. So S equals ut, 40 equals 14 times. Then to find cos theta, I'm going to draw myself a little right-angled triangle it tells us in the question that tan theta is a half. And so if I draw my right angle triangle there, there's my theta, well, opposite over adjacent, 1 over 2. 1 squared plus 2 squared is 5. So root 5 is the hypotenuse. Therefore, cos of theta is going to be 2 over root 5. It's going to be that many lots of t. So to find t, we can divide 4t by 14 lots of 2 over the square root of 5. And that comes out as 3.19 seconds. Then jumping to the vertical direction, our initial velocity is going to be 14 sine theta. Our t we now know is 3.19. The acceleration is going to be due to gravity, so minus g, or minus 9.8. And we're looking at the displacement. So s equals ut plus a half at squared. So s equals 14 times 1 over the square root of 5 times 3.19. Plus a half times negative 9.8 times 3.19 squared. And that comes out as negative 30, so it's 30 meters below where it started. And so our height, h, is going to be 30. For part B, to find the maximum height, we're going to keep working in the vertical plane. So we will have an initial velocity of 14 sine theta. We want to know at what point it's at its maximum, so that's when its final velocity will be 0. The acceleration is still negative g, and we're working out the displacement. So I'm going to use v squared equals u squared plus 2as here. Zero squared equals 14 lots of 1 over root 5 squared plus 2 times negative 9.8 times the displacement s. Then if you bring that will come out as minus 19.6 s. If you bring that onto the left-hand side, we'll get 19.6 s is equal to, when you square the 14 times 1 over root 5, you get 196 over 5. So divide both sides by 19.6, and you get that s is 2. So the maximum height above the ground is going to be that 2 added onto the height of the cliff. So that maximum height is 32 meters. Question 6 is where we've got it's not a ladder, uniform rod. It's a bit like a ladder leaned up against the wall. B is frictionless. We do have some friction at A. Just going to add forces to the diagram there. So we've got the normal reaction force at A, we've got the normal reaction force at B. We've got the 2m mass that's attached at 0.5a up the ladder, and then the mass of the uniform rod acting through the center because it's uniform. Okay, to find R in terms of m and g, well, we're going to resolve forces in a vertical direction. So the forces going up are R, and the forces going down are 2mg and mg. So those are going to be equal, and 2mg plus mg is 3mg. For part B, we're going to take moments about A. So the clockwise moments about A. The first one I'm going to consider is the 2mg. That's where the mass is fixed on. So the clockwise moments of that 2mg is going to be 2mg times by, and then the distance from the pivot point, that's 0.5a, and then it's going to be times sine of alpha. For the middle point of the mass, that's going to be mg times a times sine of alpha. Those are my two clockwise moments. My anti-clockwise ones are going to be that normal reaction at B. It's going to be S times by 2a cos of alpha. Simplifying the left-hand side, joining them together, we're going to get, they both become mg sine alpha. So when we add them, we get 2mga sine of alpha is going to be S times 2a cos of alpha. Dividing both sides by 2a cos alpha, we get S is equal to 2mga sine alpha all over 2a cos alpha. And the 2's cancel, the a's cancel, and the sine over cos becomes a tan, and we get mg tan alpha, which is what the question wanted. Part C, it tells us that the point B becomes a rough wall, so it's going to apply a frictional force. Part of that frictional force, or essentially it's going to be pushing upwards, so it gives a bit of sort of upwards, extra upwards force, and so the normal reaction force at R will be less to counter the sort of the 3 mg of weight acting from the mass in the uniform rod. And so our value for R, the new one, R1, will be slightly lower. So my statement is that R, the original one, will be greater as the new frictional force at B will provide additional upward force. Okay, on to D. So we've got an additional mass now attached. So I'm just going to add some forces onto the diagram. So we still have the 2 mg coming from that original mass. We've got the force from the rod acting through the middle of mg, and then we've got a new force at B of 3 mg acting downwards there. So the wall at B has gone smooth again, so there's no forces acting up or down there. We're going to have a frictional force, which is at limiting equilibrium at A, pointing towards the wall, and the normal reaction force. Resolving vertically, the normal reaction force will be the 3 downward forces added together, so 6 mg. And then we'll take moments about A. It's very similar to the previous question, actually just with one extra little bit. So we're now going to have 2 mg times 0.5 a sine beta. It's from the mass that's attached there, and then the midpoint of the rod, so mg times a sine beta, plus, and then the new mass that's been attached at the top, so that's 3 mg times by 2a, it's 2a away from the pivot point, sine beta. And that's going to be equal to, I haven't actually labeled it on this diagram, but I'm still going to call it S. It's going to be S times 2a cos beta. Simplifying the left-hand side and collecting everything together, we'll get 8a mg sine beta. And that's going to be equal to S times 2a cos beta. Dividing both sides by 2a cos beta, we can get the normal reaction force at B. Our S is going to be 8a mg sine beta all over 2a cos beta. And lots cancels there. The 8 over 2 becomes 4. The a's will cancel. We still have an mg, and the sine beta over cos beta will become tan beta. Tells us that tan beta is a half in the question, so 4 times a half is 2. our normal reaction force at S is 2 mg. Okay, so resolving horizontally now, the frictional force keeping the ladder from slipping is going to be equal to the normal reaction force we've just calculated. So the frictional force will be equal to 2 mg. Using F equals mu r, the frictional force is mu times r. We've got 2 mg equals mu times by the normal reaction force r we calculated at the start of part D, which is 6 mg. So dividing both sides by 6 mg, we get mu equals 2 mg over 6 mg. The mg's cancel, giving us a third, which is what we wanted. Well done if you got that one. Bye.